these concepts would be slightly extended for the independent events. So P of A union B, as I said, is basically P of A into P of B given A has happened. If A and B are two independent events, whatever has happened with A has no impact with B. So that's why I would write it as simply P of A into P of B, because P of B given that A has happened is same as just P of B if A and B are independent. What do I mean by independent events, right? Let's talk about this in normal life. So let's say I flip a coin, or toss a coin and roll a die, right? So let me define event A is getting heads, and let me call about this as getting an even number. That's event B. So if I ask you what is the probability of getting heads and getting an even number, it's asking me to find out P of A intersection B. So does the coin showing heads or tails has any impact? Does it have any impact on what I get to see on the die? No, right? Just because it's showing head, the die will not start to suddenly show even number or odd number, or it will run away from some particular number, right? The probability of whatever is being shown here is going to be same irrespective of what I get here. I flip a coin, I get a heads or I get a tails. It has nothing to do with what I get here. That's why these two are independent events. Getting heads has no impact on me getting any result in the die. That's why P of A intersection B is simply P of A into P of B. Because P of B given that A happened, is it heads or tails? See, let's assume I flip a coin, right? There are two possibilities, heads or tails. What is the probability now if I got head of getting even number? It is still 3 by 6. 2, 4, 6 are my favorable, total is 6. Even if I get tail, the probability of getting even number is 3 by 6. It won't change. That's why they are independent. Unlike what we have seen here, right? If I pick a green, the composition will be different. That's why the probability is different. If I pick orange, the composition is different. That's why the probability of getting orange is different. So there is the impact of what I do in my first event on my second event. That's why these two are not independent events. A and B are dependent events in this situation. That's why I have to do all of this. They are independent events. I simply multiply the individual probabilities, and that is A intersection B. Then there's something called mutually exclusive events. That is, if A happens, B cannot happen, and if B happens, then A cannot happen. These are called mutually exclusive. Only one of the two can happen. That is, let me define A is getting getting even number in a roll, and B is getting odd number in a roll. Right? If A happens, B cannot happen, right? Getting even number is getting 2, 4 and 6. Getting odd number is getting 1, 3 and 5. A intersection B is nothing, it's an empty set. So P of A intersection B is bound to be 0. I cannot see a case where both these events can happen simultaneously. Only one of these two can happen. Those are called mutually exclusive events. That's why P of A intersection B is 0 for that. A can solve 60% of the questions in a book and B can solve 70% of questions in the same book. What is the probability that at least one of them will solve a question selected at random in the book? So I'll say event A is defined. Okay, let me define event A is basically, I'm not using this A. These are two people A. Let me call this as Amit and Balu. Something like that, okay? Just to make it easy for you. So event A is basically getting or basically solving question, right? Amit solving the question is event A. Event B is Balu solving the question, right? So what is the probability of A happening? If Amit can solve 60% of the questions, so basically he can solve 60 out of 100 or basically 0.6. Probability of B is Balu can solve 70% of the questions in the same book. That means his probability is 0.7. If I pick any one question, his probability of solving is 0.7, and for Amit it's 0.6, right? This is clear. Now the question is asking what is the probability that at least one of them will solve a question. At least one of them solving a question is this, P of A union B, right? Either A solves or B solves, or both can solve, right? A or B. That's what at least one of them solving means. So that is basically P of A plus P of B minus P of A intersection B. I know P of A is 0.6, I know P of B is 0.7. What is P of A intersection B? This is something they have not given directly. But what you need to understand is this. Let me ask you a simple question. Does, the ability of A solving a question or Amit solving a question, does it have any impact on Balu's ability to solve a question? I'm just repeating again. Will there be any impact on Balu's ability to solve a particular question based on Amit's ability to solve the same question? That is, if Amit can solve a question, let's say question number 1 can be solved by Amit. Would that have any impact on Balu's ability? Would that say anything to me that yes, Balu can also solve? Or maybe no, he cannot solve? No, right? I cannot comment on that. Because A's ability is his own ability and Balu's ability is his own ability. These two independent things. Right? And that's the reason why P of A intersection B is simply calculated as P of A into P of B, because they are two independent things. What is the chance of Balu solving this question has no impact on Amit's chance of solving similar question. So if I ask you what is A intersection B, it's our independent events. A and B are independent events. So I simply do the multiplication, right? So this is 0.6 into 0.7. So it's basically 0.42. 0.6 plus 0.7 is 1.3. 1.3 minus 0.42 is 0.88 is the answer. Right? So what is the probability that at least one of them will solve a question is 0.88.